Does it make sense? Okay, so I'm giving an entire talk on just how to figure out the correct number of factors to extract, which seems weird. It's not a talk on factor analysis, just that one decision, because it can be a pain to make. But as a tiny bit of background, with EFA, the idea is you might be doing it on a scale that you're using for the first time, but if you're making a scale, you curate an item pool, collect data on that item pool. If you're going to do EFA, the simulation study suggests it starts to stabilize around 150 people. It gets a lot more stable around 300, basically because you're dividing up the correlation matrix, and the correlations get a lot more stable with more subjects. When you run EFA, it identifies clumps of items or factors that are correlated enough that they seem like they might be measuring the same thing. So if you're using it to create a scale, you can use it to identify items that might form subscales. You can also throw into your item pool measures that you don't want your measure to measure, like conceptual boundary, and use that as a way to make sure the items you're considering are not accidentally measuring something else. And whenever I use a scale somebody else has made for the first time, I run a factor analysis on it just to make sure in my data, it actually makes sense to score it the way they tell me to score it. And 3 times out of 4, it doesn't exactly. What EFA is doing, it's taking your correlation matrix, your item-to-item correlation matrix, and eigenvalue, eigenvector, decomposing it. Not that you need to know the math for that or anything. But it essentially finds the biggest clump of covariance, shared variance among a set of items, and extracts that as an eigenvector. The vector tells you which items contribute to that to the most, and then an eigenvalue, which represents out of all of the variance in that correlation matrix, how much that factor is accounting for. Does it make sense? You have 3 key decisions to make when you're running factor analysis: how to extract it, although that's not much of a decision anymore. People used to prefer principal components analysis if you did not know, if it was the first time, if it was truly exploratory. But simulation studies have shown that in smaller data sets, in analyses with fewer items or with items that don't load well, principal axis factoring is more likely to give you the correct result than principal components analysis. So it's almost impossible to submit a PCA, a principal components analysis, to a journal without a reviewer complaining. Even if you have a big enough data set and a robust enough factor structure, those 2 extraction methods give you exactly the same results. But reviewers don't remember that. They just think PCA bad. You also have to decide how many factors to extract, which is what we're talking about today, and how to rotate the extracted factors. The Tabachnik and Fidel, my favorite multivariate textbook, strongly recommends starting with oblique rotation, allowing the factors to correlate. If you extract factors and they turn out not to be hardly correlated at all, then you can shift to orthogonal rotation, but you should always allow them to correlate. So I'm focusing on the middle question. Why is it so hard to know the number of factors? Because so many things affect it. Sample size, how many factors are in that set of items, how many items per factor you have, and how robust that structure is. It's easier to extract a factor if the items are strongly correlated with each other. Then it's super easy to see them, and you'll reliably see them. Does it make sense? If they're weakly correlated with each other and there are not very many of them, shocker, it's much harder to reliably extract them. Fair enough? Also, what's become clear in the last 5 years, if you have factors that are really strongly correlated, like hopefully your items are loading on your I'm jumping ahead a bit, but when you extract factors, you get loadings. You see, oh, look, these 5 items correlate 0.7 or 0.8 or 0.9 with this factor. They must be in that same group, creating that subscale. But if you're extracting multiple factors and the factors are correlating 0.6 or 0.7 with each other, it gets harder for some of these statistics to figure out, oh, there should be another factor. Does it make sense? So it's that collinearity amongst the factors can really mess things up. And personally, that's affected about half of the measure development papers that I've published. Much to my chagrin, because then I have reviewers insisting that I run parallel analysis and map analysis, and they never agree with the number of factors that I want to assume, or they rarely agree. But I'm giving this talk because there's a new technique that does agree, and there's nice evidence suggesting that it's better. So how to decide on the number of factors? So there are some very simple approaches. Looking at the scree plot to see where you go from linear scree to things jumping above it. Using the Kaiser-Guttman criteria, extracting anything with an eigenvalue greater than 1. Or just testing, extract 1 factor, then a separate run, 2 factors, then 3, then 4, then 5, and stop when the new factors have no items on them. But there are statistical approaches that take a more systematic approach to this: parallel analysis, map, and EGA. So I'm going to be showing you data from a study when we made a process measure for ACT. So acceptance and commitment therapy is a third wave CBT. And with a series of visualizations, metaphors, and exercises, in-session exercises, ACT therapists target 6 dimensions of psychological inflexibility, rigid emotional responses, or responses to difficult situations that make them worse. And they try to foster 6 corresponding dimensions of psychological flexibility. So I'm not going to go into all of these, but these are the 6 dimensions of inflexibility. These are the 6 dimensions of flexibility. And I spent 3 years with J.C. Rolfs, curating a pool of 554 items, giving them across 3 studies to over 3,000 people to create a 60-item scale with 12 subscales, 1 for each of those dimensions, called the MPFI. And this is, obviously, those dimensions of flexibility and inflexibility are correlated with each other. It's important that we allow them to correlate. So when we ran the factor analysis, we used oblique rotation. So this is the pattern matrix. This is the matrix that you always see. And I know you can't see the numbers. It's okay. Their loadings are really quite nice. The loadings in the blue shaded cells tend to be between 0.7 and 0.8. And all of the off diagonal loadings are super close to 0. This is how much each item correlates with the unique part of each factor that's unrelated to the other 11 factors. That's why they call it a pattern matrix, because the pattern pops out beautifully. And the MPFI, given all of that effort that JC and I put into making it, has a really robust 12-factor structure, 5 items per factor. The items will really correlate with each other really strongly within each subscale. So simple approaches, so that we're going to use that data and see how well these different approaches say, yeah, you should extract 12. Does it make sense? So you can create a scree plot by plotting the eigenvalues. If you have 20 items, or in this case, 60 items, it will generate the eigenvalue eigenvector decomposition will create 60 eigenvalues. If you're, I don't want to get into the weeds, but the sum of all of those eigenvalues will add up to the shared variance across the items. So you can use a scree plot, and sometimes, usually if you have smaller numbers of items, the scree plot will actually help you see where the linear scree is and where things jump out and represent such big eigenvalues above that scree that they must represent real factors. There's also the Kaiser-Guttman criteria. An eigenvalue of 1 would be like one standardized unit of variance. So it's probably representing just one item. And we're not interested in single items. We're trying to find clumps of items. Does it make sense? So Kaiser-Guttman just says any eigenvalue less than 1, we don't care about because it's not going to be a multi-item factor. Does it make sense to everybody? So that's what this is what it looks like. This is an EFA on 24 items, so it's 24 eigenvalues. But you can see the first two really jump out above that linear line, and the rest of them just form this linear scree gradually decaying towards 0. Does it make sense to everybody? So if you have a scree plot this clear, and sometimes when you're just running a factor analysis on the items of a single scale, it can be this clear. You can trust the scree plot. It will tell you the right number. That you'll notice the Kaiser-Guttman in this case, this was a 2-factor scale. So 2 factors is the correct answer. The Kaiser-Guttman criteria, exactly 2 of the eigenvalues fell above 1. So both criteria argue for 2 factors. Make sense to everybody? Now, if that just would work all the time, we wouldn't have to have this lecture, but it doesn't work all the time. I also already mentioned this. You can just sequentially increase the number of tests, every possible number of factors, until you start getting empty factors, factors where no items are loading on them. Obviously, then you don't need that many factors. Does it make sense? And they can be completely empty, or they could have 1 or 2 items on them. Reviewers are okay saying we dropped it because it was just 1 or 2 items. So this is an example. If I hadn't looked at the scree plot or looked at the Kaiser-Guttman criteria, and I tried a 1-factor solution, a 2-factor solution, a 3-factor solution in that previous data, on that scree plot, the data that created that scree plot. When I ran a 1-factor solution, the solution would account for less than half of the variance in the correlation matrix. When I ran 2 factors, suddenly it would probably account for more than 50% of the variance, and all of the items would show nice strong loadings on respective factors. Does it make sense to everybody? When I specified 3 factors, if I'm lucky, then the 3rd factor would just be complete. No item would be loading on it the most strongly. If you did that, then that would also suggest 2 factors. And that's usually a pretty compelling argument for reviewers. If you say, we extracted 4 factors because when we extracted 5, the 5th factor had nothing on it. They can't really accuse you of oversimplifying your data, your findings that way. So they work well if you have no more than 25 or 30 items, these simple methods. It works well if you have fewer factors, so it's not so complicated. And they work well if you have a really robust factor solution. So, and that's always the case. Factor analysis is a lot easier to do and a lot less ambiguous if you have clumps of items that really strongly correlate with each other, because they will reliably extract. So I'd say factor loadings like pattern matrix or structure matrix loadings, or if you're doing orthogonal, just factor loadings of 0.7 or higher. And only modest between factor correlations, like different factors correlating 0.5 or less. Does it make sense to everybody? Nice discriminant validity. So I already showed you this, on these 24 items, this worked really well. That this 24 items of a 2-factor scale worked really well. But you go to a 44 item scale, and this is what usually happens to your scree plot. The more items you have, the more gradual and curved that transition from scree to not scree becomes. And it's like, where in those pink or red things do you say, okay, this is where it's scree? It's just ambiguous. So when simple methods aren't clear, we're forced to turn to statistical approaches. Parallel analysis being probably the one that reviewers have asked me for the most. So we'll start with parallel analysis. The idea is, I said this is difficult because every factor analysis, you have different number of items with different number of answer choices, with different numbers of subjects, with different numbers of factors. All of those things go in to trying to figure out what to do. So you make 100 parallel data sets that has the exact same numbers of those things, but they're purely random. There should be no factors in there. All of them should be uncorrelated with each other. So you create if you're doing a 44 item analysis, you create 100 data sets with 44 items. And if your real sample has 400 people, then all of those 100 data sets would have 400 people. Does it make sense to everybody? But they're purely random. There should be no real factors. Then you run factor analysis on all of those 100 data sets and extract the eigenvalues. Those are eigenvalues you get from junk data, random data. And so that gives you a threshold. You take the 95th percentile and you say, okay, out of these 100 first eigenvalues, the 95th percentile is 1.4. So anything above 1.4 on the first eigenvalue must be real. The second eigenvalue, those 100 second eigenvalues, the 95th percentile is 1.2. Anything above 1.2 on the second eigenvalue is real. Does it make sense to everybody? So it turns into a sort of a sampling distribution of, if it exceeds this, we're going to believe that it's real. Make sense to everybody? And I'm going to show you this on data in a second. Okay, the second technique that I'm going to talk about is minimum average partial, MAP. When you when you extract a factor, it's really, they're doing it with an eigenvector eigenvalue decomposition. They pull out the first eigenvalue in vector, and then they create a residual correlation matrix. That's the rest of the correlations without that first factor. Does it make sense to everybody? And they look at how strong are the square of those correlations, the average of those square of those correlations. You want to do the square because you want a strong negative to count just as much as a strong positive. So you square it just like you do with a variance. And the idea is you can track, as like in this example, on the on the fourth extraction, it dropped to a low point. And then it sort of stayed low until about the 9th eigenvalue. And then after that, it started increasing. So the correct number of factors to extract would probably be 9, but it would need to be somewhere between 4 and 9. Does it make sense? The new technique that I'm going to introduce to you is exploratory graph analysis. This uses network analysis. So you have to use R to do it. You can't do it in SPSS. And it's just like, if you have read network analysis papers, it's just like regular network analysis, except you're using a community walk trap algorithm to look for it's like bringing cluster analysis into network analysis. It's looking for little clumps of items that are so tightly correlated with each other, have such strong, unique links to each other, they probably are representing the same thing. So it's looking for little communities, which essentially we would call factors. And I'm going to go into Galeno and Epskamp toward the end of the talk and show you the simulation results they found. They simulated this against parallel analysis and map and found EGA gave more accurate results, especially if your factors were really correlated with each other. And this is what this is. Actually, this is what I'm going to show you the code for generating this EGA analysis. So how do we do all this? I'm not going to take you click by click through how to get this code in SPSS. Although if you were to paste this into a syntax file and add your variable names, it would work just fine. But I'm not going to, since it's not really an EFA lecture, but I will explain a few basics of what's going on in this code. By having extraction PAF, we're using principal axis factoring rather than principal components analysis. SPSS defaults to principal components analysis, by the way, because mathematically it's simpler. There's one and only one solution. It doesn't have to iterate. So if you're going to have any convergence problems, you don't have them as much with PCA as you do with EFA. But now that reviewers freaking hate PCA, understandably, it's something that you have to switch. You always rotate a solution, and there are two options for oblique rotation: direct oblim or Promax. As long as you have a robust factor structure, doesn't really matter which one you select. So I'm just going with Promax here. So that'll allow our factors to correlate. We're specifying 12 factors. This is how I got that pattern matrix that I showed you a little earlier. And it doesn't automatically give you a scree plot, but on the options you can ask for it to give you a scree plot, and that's what this purple line is doing. And there's another little, under the options, there's a little checkbox that you say, please sort the output table by size of loading, because it makes it a lot easier to read and interpret rather than having the lines all jumbled up. So that's what that does. So this is in study 2 of the development study for the MPFI. And you can see when we specified 12 factors, there was beautiful, strong loading patterns on the factors and very little cross-loading. At least once you control for the correlation amongst the factors, there's not much additional cross-loading. So if we use a scree plot, this is the scree plot for that analysis. It's 60 items, and you can see probably the first 4 eigenvalues, you can convince yourself they're sticking above the scree, but after that, there'd be no way to know that 12 is the right number. Once you start getting, and when I don't often have 60 item pools, I don't often have 60 item scales, but I will sometimes have 40, 60, 80 items in a pool when I'm making a scale. And I still have this exact same problem. Once you start getting that many items, the scree plot is just a gradual transition. The Kaiser-Guttman criteria, there were exactly 8 eigenvalues greater than 1. So it's saying extract 8 factors, which is not the right number either. It should be 12. It's actually a little odd that in this, what normally happens is, I'm going to go back a few slides. this is what normally happens. If when you have like 60 or 70 or 80 items, can you see how the scree, the linear scree, starts exceeding 1? So oftentimes, if you use the Kaiser-Guttman criteria, maybe you have a 4-factor solution that's the best fit, but it'll say extract 11 because your scree has gone above 1. So usually with a lot of items, Kaiser-Guttman is almost always, for me, an overestimate. But with AMPFI, it happened to be an underestimate. Sequential testing with the MPFI actually worked pretty well. When I extracted a 13th factor, which is that final column in yellow, no items loaded on it.
What criteria are you using for deciding a load?
None of those numbers are above 0.14. So
one would never use that as a criterion.
I mean, I could say 0.5, 0.6, 0.7. It would still, none of them would load on it. Does it make sense? Like they're all crazy close to 0. So
the other factors have loadings greater than 0.5?
Yeah. I mean, the lowest loading, I think one of them is like 0.48 or 0.42, but most of them are like, let's see, 0.7 to 0.88, 0.65 to 0.84, 0.93 to 0.79, 0.90 to 0.83. And then the rest of the numbers are just 0. Does that make sense? So when we look at, oops. Let me do this. When we look at this column, we can see it's just a whole bunch of really low numbers. Does that make sense? I actually use the conditional formatting thing where it shades from the highest number in dark blue to the lowest number in dark red. So the fact that none of them all of them are super pale and close to white suggests that they're really low. I should have mentioned that. Okay. So the scree plot was uninterpretable. The Kaiser-Guttman said 8 factors. Sequential testing actually said 12 factors, and that's in the paper. That's part of that's one of the ways we convinced reviewers that we had the right number of factors. So now I'm going to show you parallel analysis. I'm going to tell you that Brian O'Connor has a website with all of this code on it. That's where I found it. The code is actually in these slides. So you don't even have to go there. You could take these slides, highlight that, paste it into SPSS and adjust it for your own stuff. But you can also go to his website. So this is the code for, he has a SPSS syntax file, parallel.spss. And the only part that you have to change is right here at the beginning. So I'm going to zoom in on that. So you need to tell it what your sample size is, how many variables you have, how many data sets you want it to make, and what percentile you want it to give you. Because it's going to run all of those factor analyses and all of those random data sets and just spew out the 95th percentile eigenvalues for you. So you could ask for the 99th or the 90th. I don't know. I always ask. Even if you ask for the 0.999, it's about the same as the 95th percentile. They're really close to each other. Now, because I know I'm going to be running a principal axis factoring, an EFA, not a PCA, in the actual data, I initially tried using Brian's code on this last one, setting it to 2. please use principal axis common factor analysis to generate the eigenvalues. Every time I did that, and I tried with more than one data set, the eigenvalues were a lot lower and they became negative at a certain point instead of sort of drifting down towards zero, but not becoming zero. Shouldn't have negative eigenvalues because that's like negative variance that you're talking about. So it was a Hayward case. But when I set it to 1, which is what he recommends you use anyway, then the eigenvalue, the 95th percentile eigenvalues totally made sense. So I would just leave it on 1 if I were you. Oh, and I just explained all of those. Although here I have 2 highlighted as if I'm telling you to do that, but ignore this and do principal components. Sorry, I didn't get that one change made. So I'm going to pull up SPSS. I have my data set, and it has, these are they start here and go on for a ways. These are my 60 items of the MPFI. This is from the data set from which we created it, which is why they have crazy little numbers. And I'm not going to go into what all of those little acronyms stand for. But those are the variables that we submitted to the analysis. And so this is the EFA that I ran to get that pattern matrix that I've already shown you. When you run it, one of the first tables it gives you is total variance explained. When you run an analysis, an EFA, you want it to explain at least 50% of the variance. When you extract 12, it explains 75.8. For the people back there, I'm sorry. I know it's teeny tiny numbers. It also shows you all 60 eigenvalues extracted. Here's the scree plot for that, which I just showed you on that other slide. And, well, actually down here. And this is the pattern matrix that I pasted into Excel and then did that fancy formatting on. To change it to 13, all I did is change this factors to 13 right here. If you wanted to use the Kaiser-Guttman criteria, which is not a bad idea to like the first round, if you don't know how many factors you're going to get, you would just change the word factors to min eigen and the number in parentheses to 1. So extract it if it has an eigenvalue of 1 at least.
You don't actually have to say anything because it defaults to 1.
Yeah, if you're going through the window to create it, you can just not touch that and it will put min eigen 1 there for you. So here is our parallel analysis syntax, and you can see we've changed these numbers to what we talked about, and this is still on principal components analysis. With this massive data set, the eigenvalues that came out of the PCA were nearly identical to the eigenvalue, like to the first 3 decimal places, to the eigenvalues that came out of principal axis factoring. So that supports Brian O'Connor's assertion that you can use it should still be appropriate. So I'm going to scroll all the way down there and then hit run. And here it is giving us the 95th percentile eigenvalues for the first eigenvalue out of random data, the second, the third, the fourth, the fifth. This is our, you need to cross this line boundary. Does it make sense? So coming back to the slides, I took that, pasted these numbers into here, and then the eigenvalues from the EFA output here. And you can see after the sixth eigenvalue, which is still above that threshold line, the seventh, 0.123, is just below what you can get from random. So this is saying extract just 6 factors. Does it make sense? And this is looking at that graphically. So the purple line is our exceed this random threshold, and the blue line is what we got in the data. And that seventh eigenvalue is just a teeny tiny smidge lower than the threshold. Fair enough? Now, that first syntax used, I do need to pick this up. That first syntax used purely random data. Brian O'Connor wrote this next syntax based on some papers that came out more recently, where you give it your data set and the 40 variables, and instead of making new it makes new data sets, but instead of creating brand new random numbers, it just randomizes the numbers within a column. So it maintains the skew and the kurtosis and the exact distribution of responses that you got with each item, but randomizes the rows so that they're not going to be correlated anymore. Does it make sense? Which I thought was super cool. And I was really excited to see it. It tells us to also extract 6. And gives almost exactly the same 95th percentile exceed this threshold, like pretty much the exact same numbers. But I've highlighted it's the sort of the same questions, except for this one at the bottom, the last one that's in green. Well, that looks green because it's blue on top of that yellow wood. Compute rand type equals 2. That makes it randomize your data, which takes longer, but I mean it still runs really fast. And it actually also gives you the eigenvalues. So these are the eigenvalues it got with principal components analysis. These are the eigenvalues I got with principal axis extraction. And they're not exactly identical, but they're fairly close. And the threshold where the eigenvalues drop below the exceed this threshold is exactly the same. Does it make sense? So even that fancier brand new version of parallel analysis with randomized permutations, it suggested 6 factors. Okay, this is the code for map, and where you have to change the code is a little further down. Their map just needs a correlation matrix. And there are many different ways to give SPSS a correlation matrix. So the opening syntax, it'll be like option 1, describe a paragraph, and then show you how to do it. Option 2, option 3. I just used option 3, had it calculate the correlation matrix from my data. So this is the path to my data set on my computer. And then I just had to add the names of the 60 variables. And it would pull them in, calculate the correlation matrix. And so in SPSS, I'm not going to run the permutations of your own data. That takes a lot longer. I'm not going to run that. But if we start highlighting here in the map syntax, and go all the way to the end and hit run. It gives it gives us the eigenvalues, and then below it from a PCA, and then below it gives us the squared average partial correlations and the average partial correlate. Well, the partial correlations raised to the fourth power, averaged. And so if we look at those, originally Velcier recommended squaring the partial correlations before averaging them. And if you do that, it suggests 11 or 12 factors, really 12 factors, because that's where you hit a minimum. That's where that low number gets lowest, and after it starts increasing again. Velcier revisited this approach in 2000 in a paper in 2000 and said, no, you should raise the partial correlations to the power of 4 and then average them. If you do that, it suggests 9 factors. So the old school map suggested the right number of factors. The new map that they recommend did not. So sequential testing worked for the MPFI, and the old version of the map did, but the scree plot, Kaiser-Guttman parallel analysis, and the newer version of map did not. Why are these not working? With so many items, it drives the scree above 1. It makes the scree transition gradual, but it's really these correlated factors. So now I'm going to show this is output from that same EFA on the MPFI, but this over here is the structure matrix. So that's how each item correlates with each factor, raw correlation, zero order correlation. And you can see the positive dimensions of flexibility all correlate with each other quite a bit. And the negative dimensions of inflexibility, all correlate with one another quite a bit. There's quite a bit. And if we look at just the factor to factor correlation matrix, this scale has 2 higher order factors. The 6 positive subscales form a global flexibility composite, and the 6 negative subscales form a global inflexibility composite. Does it make sense? That's why all of those things were giving wrong answers for the MPFI. They thought it was far fewer factors because there's so much correlation. So Golino and Upscamp in 2017 published a paper validating exploratory graph analysis. It's a network analysis approach. All psychological network models use Gaussian graphical models. If they're in smaller samples, almost all of them use lasso regularization. We're actually doing okay on time. I'm giving you a tiny bit of background on network analysis. If you have a whole bunch of things that are all correlated with each other, and you want to know where are the strongest links, you can use network analysis. What it does, you give it 10 items, it will go pair by pair of items and calculate a partial correlation for that pair, controlling for the 8 other variables in the model. So you're controlling for a lot of other correlated stuff. That shrinks all of the correlations down pretty small. Does it make sense to everybody? And you use lasso regularization to take things that have gotten super teeny tiny and close to zero and just set them to zero. And they've shown in simulation studies that the way they have it programmed, it's unlikely to make you believe spurious things and also unlikely to make you miss meaningful things. Does it make sense? I mean, nothing's perfect, but it's balanced out well. With extended Bayesian information criteria to figure out what to regularize. But the difference, so it's a nice way of putting in, like I put in 20 relationship processes and then looked, most of the correlations dropped to zero, dropped out. But the ones that remained made sort of chains of possibly mechanistic pathways. Like this is really uniquely linked to this, which is uniquely linked to this, which is uniquely linked to this. So it's a way of starting to order things when it's really exploratory. The unique thing about EGA is that you use a walk trap algorithm that's looking for clusters, strong, tight clusters of nodes, of variables. That makes it more like a factor analysis. And to validate it, they made 32,000 simulated data sets where they varied the number of factors, 2 or 4. They varied the number of items per factor, 5 or 10. They varied the sample sizes from 100 to 5,000. And they varied how much the factors correlated with each other, from 0 being completely uncorrelated to 0.7 being pretty correlated. Does it make sense? Correlated close to what the MPFI subscales are correlated. This is a graphical representation of their findings. I've added the pink, yellow, and blue highlights. So MAP, this is average accuracy by each condition. So the 4 different bars are the 4 different sample sizes in each square. Does it make sense? The height of the bar is how accurate, how many times it gave the correct result. These are simulated data sets. So we know, are they putting the right items on the right factors? Are they telling you, is it telling you the right number of factors? And these first 2 rows are with 5 items per factor and 10 items per factor with completely uncorrelated. Then the next 2 rows are 5 items per factor, then 10 items per factor with low, like only 0.2 correlations among the factors. And then 5 items and 10 items per factor with moderate correlations, 5 items and 10 items with high correlations. Does that make sense to everybody? And you can see MAP doesn't have very good accuracy across the board. It's one of the worst things tested. The parallel analysis does pretty darn well until you start getting moderately correlated or high correlated factors with only 5 items. Then parallel analysis really starts to fail. Does it make sense? And on the MPFI, we have highly correlated factors with 5 items each. We're pretty much right in this cell, which is why parallel analysis was not doing very well. Fair enough? The EGA still struggles in there, but at least it's one of the only ones that has a decent chance of coming up with the right number of factors when you only have 5 items per factor. Does it make sense? So in R, this is the code this is all the code you need to run it. It's pretty simple, but it probably, how many people are really familiar with R? Okay, that's awesome. When I first started using R, I would look at this and be like, because so much, it doesn't leap out and make sense to you right away necessarily. So I've annotated it here. I'm going to go in rainbow order. Read R is the package that you need to read in a CSV file. so that we're pulling that from the library. EGA net is the package you need to run EGA. This next line, we're using the read.csv from readr, and then I specify the folder that my data and I'm saving the syntax in as the working directory, so I don't have to put complicated paths and it's a hassle. But this is the data file that I'm pulling in. And for this one, I was lazy. I used data from a paper that we just recently published. So this only has 275, but it still worked well. So it's taking this data, and with this backwards arrow, it's putting it into a matrix, a data frame for us to use. And you'll notice the very next line, we're calling a new command, ega.estimate. That's from the EGA net package. And we're saying use the data that you're going to use is the data we just pulled in, that data frame. Does it make sense to everybody? And even if you have beautiful data and your items are perfectly normally distributed, it's still item level data. It's still probably not interval data. It's probably more ordinal. So we just specify always Spearman correlations so that it doesn't assume interval data. And Lasso is the Gaussian graphical model with lasso regularization. Those are typical, even if you were running a network analysis with BootNet, you would be using those same statistical approaches. But this specifying walk trap where you want the highest modularity, that's the code that's more specific to EGA. And then once we've run that, we have our output waiting in an EGA. EGA is a complex data frame. It's not just a matrix of numbers, not just a single table. It has a bunch of tables in it. If you list it like this, it will show you the names of the variables and what groups, what communities they're in. But if you say, we're going to use EGA $ network, and that has the information for a spiral graph, not a spiral graph, a spring graph to plot the results. Does it make sense? So I'll go to R. And I know this is super teeny tiny, but I want this to be nice and big for the plot. So really, to run this, we just need these two, like I have in the slides. And then I can pull in this data. Does not exist. Wait. Oh. It's nowhere near the correct. Here, wait. What is going on? R, no, HSDG. Sorry, I thought I had this already on the right. Nope. Nope. Okay, here we go. I want this to be my working directory. And now this should run. There we go. Okay, we've pulled that data in. And now we run this. Does the walk track algorithm. And then we ask for the output. And we get this. Which shows this. And you can see it specifies 12 communities. So this is the first fancy statistical one to actually, well, I guess the old school map did as well. But this one is now specifying the right number of factors to extract. Fair enough? Now, this is the code for graphing it. So a lot of this code is not necessarily, the purple and the blue is not really necessary. I'm grouping the items based on which ones said they were different, they were in the same community. And then those corresponded to my subscales, so I gave them the subscale names so it could do a legend for me. But you wouldn't have to do that to see the output. And the blue code, I'm actually telling it different colors to do each of the communities. Otherwise, I'm using QGraph, and I'm doing the QGraph in this yellow on EGA, my data frame for my output, string network. That's where the Spring Graph information is. I'm telling it I want to do a Spring Graph. I want to use colorblind, which makes it easier for people to see blue versus red. And then I'm telling it groups is this purple thing this purple list that I just created. So if I run that, I'll run this first. And then I'll run the graph. Oh. It would be helpful if I put QGraph in. I don't think I need these other things, but I do need QGraph. And there we have the 12 communities. And you can tell, especially for the people near the front of the room, all of the D's are a little, that's diffusion, and those 5 items are making a subscale, and that's one of the communities. EA is experiential avoidance. Those are that pink color down here, and they're making a community. Does it make sense? So you can export your item data into an Excel file, into a CSV file, run these few lines of code. It will tell you 12, and use that to justify extracting 12 factors in EFA back in SPSS. Does it make sense?
Question about the graph?
Yeah.
Can you interpret the distance between the items as a measure of correlation or how close they are, or is that just unanswered?
Yes and no is the answer to that. As much as it can within a 2-dimensional plot, it tries to put things that are strongly related close to each other. But you can see many of these nodes, many of these items have lines going to 10 different things. Right. So it's finding the best position for it in respect to all 10 of those.
So for example, D4 and EA5 are closer than EA5 and EA1.
Except they don't have,
because it's 2-dimensional.
Yeah, and they don't have a unique edge going between them.
Well, it looks like there's a line.
No, that line's probably, because it would need to come from the center. That line's probably going to A5.
Okay.
Like, let's see. Let me see if I can find one. SCN, self as content 2, looks like has a direct line to inaction 5. That's a true edge. Also, I mean, I find network graphs like this only mildly useful because when you have so much covariance in there, like these items are correlating 0.7 with each other. So the links between the items in each community are nice and strong, but that shrinks all of the other lines down to teeny tiny itty bitty ones. And so knowing is this dimension more related to this dimension or not, it's almost impossible to tell. I mean, there's a bunch of lines, so it probably is, but it's harder to tell in this than it would be if you ran network analysis on the subscale scores. Okay, so I'm just going about a minute over, but that's all of the demo that I wanted to do. I just wanted to end with a little summary. So if you have simple and robust structures, so not too many factors, plenty of items per factor, and maybe no more than 30 items, then just about everything works, except MAP in those simulations had the worst track record, so I probably wouldn't bother with it. You'll notice I have bolded item loadings. Those are probably the most important column out of all of those. If your items are super strongly correlated with each other, you're going to have an easy time figuring out how many factors there are. If within each factor they're strongly correlated, makes it so much easier. Then even just having 5 items in each factor for the MPFI, the factor structure was super stable because they were so correlated with each other. Does it make sense?
But you're not including sample size in that, but in the simulation results you presented earlier, sample size.
You're right. You're right.
In the case for 5,000.
5,000.
The methods did well. Go back to that.
Yeah. Let's go back. You're right. I forgot that. I apologize.
No, I'm just trying to understand.
Yeah, I think you're right. Also, the second most important one is how correlated your factors are. Yes. But let's go back and look at sample size. Oh, and I didn't say it out loud, so I apologize. But the other thing is they showed all of the results before we do sample size. They showed all of the results for 2-factor simulations and then separately for 4-factor simulations. And the graphs were nearly identical. I didn't make another slide because it was almost exactly the same. So between 2 and 4, maybe it would have been different if it had been 2 and 10 or something like that. But between 2 and 4, there was not a whole lot of difference. But you're right. If you look within each of these,
I mean, with 100, you're really in trouble.
Yeah.
With 500.
Although with 100, Kaiser is not so bad.
Yeah, Kaiser always gets a bad rap, and it looks fairly good now.
Yeah, but and that's probably because they weren't, the way they did this, since it was 2 and 4 and 5 or 10, they never had like a 60 item scale or an 80 item scale where it would really mess the Kaiser up. Does it make sense? But here in this cell, even 5,000 didn't fix principal parallel analysis, right?
But if you look at EGA,
yeah, you're right.
Pretty sucky too.
Yeah, it got it right half the time with 1,000. Yeah, but that's at least better than 0, right? Yeah. But you're right. Sample size definitely helps. But I thought this would be helpful going over all of these things and getting a sense of when they are useful and when to use them.
What really surprises me is how